All right. What is a histogram? We talked about it last time. What is a histogram? What does it look like? Yeah. If you look at your sheet I gave you, you have it right there, which is usually how the students answer my questions. They look at the sheet I gave them. Yeah. Another name for the histogram is a bar graph or bar chart. Where traditionally the bars are connected, they share a side. So here's your categories, whatever you're looking at, whether it's male, female, whether it's a red car, white car, blue car, whatever. And these are the frequencies. Another way you can look at histograms is as a frequency distribution. Because on each of your bars, you typically have on commonly people do is at the very top of the bars, they put the values to make it easier for you to see how much they represent. They don't have to be there, but if you're going to do a report, it's much more simple because if you just had the bar like this, then what you'd have to do is try to see where does it go exactly over there. But if it's labeled for you right there, then um, you can see what it represents. What goes on the horizontal axis? If it is time, but yeah, it's not just time, but it could be characteristics like how many students have blonde hair, red hair, white hair, black hair. You can look whatever characteristics you're looking at, those are your horizontal axis. Because the vertical axis is the frequency. So these are your characteristic trait being observed. Why is this one of the most commonly used data representations? Yeah, it's all right there in front of you. Well, what's missing in this? What's missing? Do we know what A, B, and C are? Unless it's listed, what do you need to have with your chart? A key, what we usually called the legend. A will represent blonde, B, red, C, brown, D, black hair. We're looking at hair colors, which actually we can do that because we said next time before you come to class, wherever you're coming from, actually from the class you're in before this, we can say, hey, let's everybody observe one trait about those students. And then we can come back, we could bring all our data together, and then we can create the stuff. All right. So one thing that we could do is look at your other classes. How many students have cell phones out during class and actively use it, even just to look at it during class? Even though in this class, you're not supposed to have anything on your table other than your notes. Because if I see anybody having a cell phone out looking at it, we're going to have a quiz. And putting it in your lap's not going to help either, because what are you doing there? If it rings or anything, you're just going to look at it there, and then that pisses me off even more, because you can't be honest with me or yourself. So again, if I see anybody checking their phone during class, we're going to have a quiz over anything from day one. So I'm just trying to get you guys away from that. Actually, I just read an article that said that students, the obsession students have with cell phones in schools is I don't say a psychological disorder, but a chronic disorder students have. In the old days, what do the popular students do in class? What do they always do in class? The most popular students. They always talked. They always had notes being passed. The non-popular students did what? Kept quiet and sat there. Now the cell phone with emails and stuff like that, or your Instagram or whatever, now gives everybody a chance to try to be popular. So that's what they're looking at, is it's just a way that the uncool kids are trying to be cool now. But again, the end result is nobody's getting anything done. So that's why in all my classes, I say no cell phones out, period. Unless we play a game. So if this is a frequency, how would a frequency distribution work? What is a frequency distribution? We talked about it last time. What does that look like? That's a relative frequency. Relative frequency goes into percentages. And you're right, we could also do that here. We can see how many we have total and find exactly what percentage those are. But what is a frequency distribution? How does that look? This is a frequency distribution. How does that relate to the histogram? Well, look at it. In the histogram, how tall is A? In the frequency, where's A? How tall is A? Yeah, so since A and B have to share a wall, A just goes like this. Where's B? B goes all the way up to 4. And then C, and then D. So that's the relationship. Let's go one step further. Cumulative frequency diagram or cumulative frequency chart. You won't find it anywhere. So instead of trying to flopping through everything, just listen. You're going to spend too much time. With the name of it, what do you think that says? What does cumulative mean? Total. Cumulative means total. More so, it means a running total. And a frequency means how many you have. So if we looked at our data, we have the characteristics and we have the frequency. And then here we have the cumulative frequency. So this is A, this is B, C, D. A had 2, B had 4, 3.8, and 1. So the cumulative frequency is a running total as we're going along. Yeah, stop looking. So all you're gonna do is waste time looking for it. The cumulative, you should be, so if you can't find the stuff, this is where you should be writing stuff down in your notes. Instead of looking for this all the time, you're wasting too much time doing that. Take out a piece of paper and write down your notes. So in the running frequency, the cumulative, in the running total, A has how many? 2. Now the next one is A and B. Together they have what? Yeah, there's 2 there plus 4. That makes it 6. Now A, B, and C has how much? 9.8. Because you take this number, add it to that, you get that. So the last one would give us 10.8, because we take this number, add 1 to it, and we get 10.8. That's our cumulative frequency distribution, or chart. Yes, we're adding the numbers as we're going down the list. And again, we check it to make sure we're supposed to have 10.8 numbers. Yeah, and we have 10.8 numbers. That's a running total. So what happens here, so at A, we start off at 2. So it goes from 0 to 2. When we get to B, now we have 6. Now at C, we have 9.8. And then at D, we have 10.8. So what good is a cumulative frequency distribution or cumulative frequency chart? You can see at what intervals do we have most growth? Where's the steepest line? Between which 2 numbers or which 2 letters? Where is the most steepest? Yeah, between A and B. That's the steepest, so that's when most change occurred. Is that readily observed here? Yeah, kind of. You just see that there's a big gap. So you look for who's got the biggest gap. That's a small gap. Well, that's a pretty big one, but it's going wrong direction. That's a loss. I want to see how many increasing we have. So in this chapter, we're going to start dealing with calculations and analyzing data sets. What we look at is how do we interpret a histogram? Observing the shape of our data. We can't do anything just by the numbers themselves. We have to put it in a picture. So when we look at the shape, we look at our graph, our histogram. In order to be able to do calculations and, and analyze our data further, because graphs are great, it tells us a lot, but we need to know more information, and that comes from calculations. We look at the shape of it. If you look at this small graph, we notice that there's a rough bell shape. We call that a normal distribution. A normal distribution is when the shape of the graph representing our data has a general bell shape. What does a bell look like? You've ever looked like the Liberty Bell? Okay, that's one thing you say. Yeah, if the data looks big, you can do it. No, that's not. What does the shape of a bell look like? Well, it starts off and then it goes up. Then you have the top of the bell where you have the hook, the loop, and then it goes back down and it has to be a mirror image of itself. That's a basic shape of a bell. Because if you drew a circle around it, there's your bell. It looks like a bell now. That's why they call it a bell-shaped curve. The beauty of a bell-shaped curve is that from the middle where you hook up the cable to hang it up on the rafters, we know that it's evenly symmetrical. If your data is bell-shaped or normally distributed, then we can start doing stuff, we can do some calculations on it. So this is the optimal. If your data looks like this, you're in real good shape. Because now what can happen? We can look at being uniformly distributed. What does it mean uniform? In a histogram, the heights of the bars are relatively uniform in shape, in size. So in other words, your data could look like this. Does that tell you anything? No. So it's the data represent by normally distributed, and they occur approximately the same frequency. Can you do anything with it? Not really. So everything's the same. Give me an example where that's true. Give me an example where something has the data is uniformly distributed, or an example you can use. What's that? What do you mean? Okay, go with that. Actually, that's a good question. If you get to an intersection of a very busy intersection and there's a stoplight, do each of these lanes have the same length of wait? Why not? You're right, they don't, but why not? Good question, good point. That's a good point. One of these avenues could be the main road, and this could be the ancillary one. But what if they're both popular, very main roads? But that's a good observation. I didn't think about that one. Do you ever think about how lights are timed when you get to an intersection? Where? Well, yeah, I said there are sensors. They're pretty much magnets underground that, depending now on the, because before they put stoplights in places, they used to have always stop signs. But then when the lines got really big, they said, okay, let's analyze this. And then what they look at is which direction do they have the most traffic? Because then what they do is certain distance back underground, they put magnets. Because now if your line is that far back, it'll trigger the light. Kind of like if you're a pedestrian and you want to cross the street, you press that button. That's what it does here. Because the further back your line is, the more time they'll need to go through the traffic light. So yeah, how about turning lanes? Same thing there. They have magnets there to see how far the line is for turning. So is it uniform or is it normally distributed? So they all go at the same time? Same length of time? No. It's it's bell shaped because what happens here, they want to average everything in at the end. Everybody has to get through the traffic. So sometimes, if you think about it, why do traffic jams occur on highways? When you wake up in the morning, go to work, you have a traffic jam. Why? Yeah, that's true. Or the city council were bribed by too many developers to let them build hotels and apartment complexes. But no, what happens is you have directions. You ever get stuck in a traffic jam, you look on the other side, it's empty? Well, because everybody, as you said, it's everybody who lives someplace, they, at the same time, they have to go to work. So in the AM, this is a traffic jam. In the PM, they're going home. So that's what another thing they look at is at what do we have to do to make these traffic jams smaller? They look at that, but they never do anything. Because the only way you could stop traffic jams like this is if you stop construction, which is what I think it's Forney. They put a 5-year moratorium on any new development, which is what Dallas should do. They should stop constructing any new buildings, period, for at least 5 to 10 years. Let the highways, let the schools, let the hospitals, let the fire and police catch up with us already. Okay, so we look at normally distributed and uniformly distributed. What about if we had this. Let's say this is the uh, number of students in a classroom, and this is the number of absences. Is it normally distributed? No, because obviously you see it's further onto one side than the other. Because typically you'll have a certain amount of absences which aren't that high, but then some students will have many, many, many more absences. What do we call those? When something shifted to one side or the other, what is that called? So you don't strain your eyes looking for it. Skewness. When something is skewed, that means it's shifted to one side. Now, what do I mean shifted to one side? Because remember, a normal distributed curve will look like that. That means the average is in the middle. It's now shifted. The average now is shifted to the left in this case. So what do you think we call that? If it's shifted, if everything is shifted to the right? That's called skewed right. There's an easy way to memorize this. And what do you think this one's called? That's called skewed left. This one is called skewed left. Now, the easiest way to memorize this, what happens here is because we're looking at where does it taper off? It tapers off on the left side. But that, again, that's a whole bunch more words you have to learn. Look at your feet. If it looks like this foot, if it looks like this foot, that's your right foot, right? So that's skewed right. If it looks like this, it's skewed left. Just think about your feet. That's the easiest way to memorize them. And so I forgot the mathematics behind them. What else are we looking at here today? Yeah, because the way our data is aligned, arranged on a graph, what is a dot plot? Just instead of looking for it, just what do you think? Just from the name itself, dot plot. What's that? Yeah, these are just putting dots where the data goes. Those are dot plots. They don't try to confuse you with the names of these graphs. So if I give you a name, think of what the name is telling you and try to logically extrapolate what the graph's going to look like. So in a dot plot, you don't try to connect them anyway. You just put them in there and see what happens. All of the data, not just the frequency of them or and put them in classes. Here you look at all the data. Here are two examples. Which one do you think you can predict what's going to happen in future occurrences? The left one, because that's what we're going to cover it at the end of this chapter. We're going to look at we'll look at something called correlation, and then another question called regression. But we're going to look at correlations. But in this case, we're going to look at, are the data points, are they normally distributed? I mean, not that it creates a bell curve, but can you represent them by relatively straight line? Yes, because the data itself, you can find a line that best describes all those. So these are normally distributed. The closer these dots get to that line, the better you can predict future occurrences of that outcome. But can you make a line prediction here? Do you think, because this one here, I could define a line that's going to give me a good chance at the future. How about this one? No. Is it going up? Is it horizontal? Is it going down? You can't do anything with that. So is that normally distributed? No. So this one is not, bless you, normally distributed. So those are the first two cases. If you can draw a line that looks at all the data and it fits in there, give or take plus or minus some of them, as opposed to, are they everywhere? Those two right there. Remember the example of the pennies? How do we determine if it's made before 1983 or after 1983? Is the weight of it, because the amount of copper versus zinc. Is this normally distributed? No, because we have two separate groups here, and neither of them we could use to predict anything. So that's not normally distributed. Is that normally distributed? Why not? Right. Even though there's a line that defines those, these ruined it for us. That's not normally distributed, because all of the data have to be in that range. Because in section 4, we're going to figure out how to determine what's the average distance from these points to that line. The smaller that number, the better it is. How about that? Is that normally distributed? Why not? But they're close to that line. Neither is this one. What's that? When this one has no line. There's the distance from each of these points to that line is very close. But are we looking at slopes? No, but you guys are right, but not for that reason. Anytime you have a cyclical pattern, you cannot say it's normally distributed, because why is it that way? There's something behind it that's taking the randomness away. Because remember, we always talk about random. Random is just that. This, as you observed, it's a predefined sequence of points that follow a pattern. And because of that, the symmetry of it makes it invalid. So that's not normally distributed. That's not normally distributed. So to determine, now, instead of, if you didn't have the pictures, if you just have the data itself, how can you determine if it's normally distributed or not? If you just have the data, what do you think? How do we determine if it's normally distributed or not? Ooh, that's a good question. What if you have 1,000 numbers? They just flip a coin to 50-50. Well, each point has an X and Y value. For example, the X could be the time and the Y could be the frequency or how much money you made or something like that. So each point is comprised of an ordered pair. Each point has an ordered pair of the X and Y components. But not by looking at the points, we can't do anything. We would then have to do a calculation. Whoa, no. No, they're all going to be, all the numbers have to be positive because they fit in the first quadrant. Good try though, but no. In section 4, we do, right. But we can only determine that if we look at all the data and determine the slope or the distance between each point and how far they vary from that line. Again, this is what we're going to do in section 4. Not today, we're going to do it in section 4. Because remember, if it's a normally distributed curve, there's a line. We have to define what is that equation of a line. So what formula do we have for equations of lines? Y equals mx plus b. What do all these letters represent? What does m represent? What does b represent? The y-intercept. In other words, if you drew this line all the way across, where does it give us the y-intercept? Why is that important? Why is the y-intercept important in this case? Yeah, that's when x equals 0. That's where everything starts. In the beginning, that's where we are. And then from there we go, either up or down or horizontal or whatever. So we need that to see where we start. This is when x equals 0. And x and y are the points or the components of each of our points. So what we have to do we have to find equations to find the slope and the intercept. That's not good. It's plugged in. But we're almost done anyway. That's what we're going to do on Tuesday. All we did. Okay, now the reason originally I was going to do 2 sections, 2 and 4 today, finish up chapter 2. But let me show you this real quick before it dies. We are right here right now. After today, we finished everything up to 2.3. We're only in the 3rd week. We have